AP Calculus AB, Unit 7, corrective. So I don't know if you guys want to check your answers real quick. If you haven't had a chance, these are the answers to the corrective. Pause the video if you need to. This is the first 3 pages. Okay, assuming you checked all those ones on the top, here are all the answers from the bottoms of those 3 pages. Okay, so let's try these problems out. See if we can get ready for a retest. All right, so let's see. First problem, just looking at the graph. Critical points are where f prime equals 0 or undefined. So they're nice flat hills. We have horizontal tangents or cusp or point or something where it doesn't. So, and they say that there's one at D. So those are all critical points. They don't have to be the top and bottom of the hill. It could be like a plateau. So that's going to be at x equals b, d, f, and I. Next one, inflection point. So I like to emphasize the concavity. It's concave down, concave up, concave down, concave up, concave down. So we're going to say the inflection points are at C, D, it changes from up to down. And F, it changes from down to up. So F is an inflection point. And H. Now, is it H or is it G? It's H. G is a 0. That's why it's there. So if it's like, well, which one is it? What else would H be? G would be a 0. So those are your answers. Relative extrema. So we have relative maxes and we have relative mins. So relative maxes and we have relative mins. So the relative maxes are at B and I peaks. Relative min, there's only one relative min at F. Okay, so D, absolute extrema. The absolute max is, it can happen in multiple places, but there's only one absolute max value. Y value is at x equals B. There could be a tie, and therefore you would have to list all of them, but absolute min is at x equals F. Okay. Decreases. Well, that's where the derivative is negative or just clearly going down. And we usually include the endpoint. So we're going to say it's going down from B to C to D to E to F. B to F. We don't split it up at 0 slopes in the middle, and we include the endpoints. And then I to J, and we include the endpoints. Where f prime is increasing, so that's looking where f double prime is positive, where it's concave up. Now, usually we don't include the endpoints or concavity, but they didn't ask us for concavity. We're just associating with concavity. They ask us, does something, where is something decreasing? So we should include the endpoints. So where's the concave up? We're going to say C to D, and we include the endpoints, brackets. Actually, sorry, concave down. Negative, decreasing. So not C to D, A to C, and then D to F, and H to J. So those are all where F prime is decreasing. Now F is concave up and decreasing. So F prime is negative, F double prime is positive. It's got to be concave up and going down at the same time. Concave up and going down, that'd be C to D. Now, is it concave up at C? No. So we don't include it, even though we include it for decreasing. At D, we would include it for decreasing, but is it concave up? No. So that's decreasing concave up. And I think that's it. It's the only interval. All right, next one. Same kind of questions, but we have the graph of the derivative. Okay, so what I usually do is kind of go through here and just mark it up. So I say, oh, well, this is increasing, decreasing, increasing. These are all derivative values. And then I'd say, okay, well, this is a critical point where the slopes are 0. And so it's going up and then down. This is a relative max. And then it's going down and then up. So that's a relative min. It's going up, but that's at the edge. So we don't know what's going on the other side. So we're not going to call it a relative max or min. Concavity. F double prime is negative. It's going, the derivative of the derivative is negative. The slope of the derivative function is negative. So that's concave down. And it looks like it's like 0 right there. So I think we have to break it up. F double prime is positive concave up. And then F double prime is positive concave up. And F double prime is negative concave down. And so then we get inflection points where it changes concavity. Okay, so inflection point would be at x equals, it says find all the values of x where f has an inflection point. Some people interpret that as like, oh, I only need to give one. Well, when did you ever only give one answer in math when there are multiple correct answers? Plus, if you read the directions carefully, it does indicate plural, the possibility of plural. So at x equals 2 and 5, relative min at x equals 3, f is increasing from 0 to 1. We include endpoints for increasing, decreasing. And it's increasing from 3 to 6. Okay, don't misinterpret this as the graph of the slope. This is the graph of the derivative. Okay, f is decreasing and concave down. Decreasing and concave down would be 1 to 2. Is it decreasing at 1? Yes, because we include endpoints. Is it concave down at 1? Yes, it's in the middle of concave down, so we would include 1. Is it decreasing at 2? Yeah, it's in the negative range, right in the middle of it. Is it concave down 2? No, that's where it has an inflection point and changes direction, so we put a parenthesis on that. We don't include that endpoint. They're on no other intervals. We can use this information to do a quick rough sketch of what the graph would look like. So kind of working backwards. And so we'd start at like, this is your initial value. So instead of doing a plus C value, that's like our plus C right there. And so the first chunk, it is going up, but concave down. So I usually kind of do just like little quarter chunks. Next chunk, it is going down and concave down. It should be smooth. If this graph is smooth, then the graph it's the derivative of should be smooth. 2 to 3, it's going down but concave up. 3 to 4, it's going up and concave up. 4 to 5, it's going up and concave up. 5 to 6, it's going up and concave down. So it should be a nice smooth graph. Okay, now I might just give you a derivative that's already done. You should enjoy that. X equals negative 3. This is, if you were to solve this, e to the x equals 1, you take the natural log of both sides to get rid of the e. Now, natural log, if it was like natural log of 3, then that would just be it, and you might use your calculator to estimate the decimal. The natural log of 1 is 0. You guys should know that. What do you raise e to get 1? Log of any base of 1 is 0. What do you raise something to get 1? You raise it to 0 power. So, and then we have x equals 1. Now, be careful. This has an even power on it, so it's going to get repeated and bounce off the graph. So we're going to do a line check. You need to label your line check. Some people have taken off points for just not labeling their work with things like this. In fact, you should write equals 0 undefined on this. If you don't write that, I'll take off points. Okay, that's important calculus work. Okay, algebra stuff you want to leave out, whatever. Now we're finding all relative extrema. On the test, I might have just said relative maxima or relative minima. That's just one or the other. Extrema is all of them. Okay, So we're going to put these points left to right, smallest to biggest, -3, 0, 1. Don't lose track of that. 1. Label it. Tell me what value you're going to test. I'm going to test far right usually on these rational functions and polynomials. I feel like that's easiest because it's positive, positive. Everything's positive. So it is positive. And then it stays positive, and then negative, and then positive. And then I like to draw these little arrows indicating the slopes in very rough fashion. It makes it very clear to me that this is a relative max, and this is a relative min, and this is neither. So our relative max is at x equals -3. Our relative min is at x equals 0. We actually can't determine what the relative maximum and values are, the y values. We just find their locations here. We don't have the original function. So there you go. Get that one right. That one is line check problem with the least amount of messy work. Now, the next one, kind of give you one of each, give you a rational, exponent one, trig one with E and stuff. Okay, so first thing you want to do on any of these problems is keep in mind what the domain is. What's the domain? Now, that's only the original function where you make this kind of call. Now, are there any square roots of negatives potentially? Like these denominators, those are roots. Those are cube roots, so it's okay. But if there were 2 or 4 or even numbers on the bottoms, you wouldn't be able to put negatives in. Any natural logs of negatives or 0? No. Any division by 0? Right here, this is going to give you division by 0 because this is a negative exponent. So you're going to have division by 0, so x cannot be 0. That's your domain. You just got to make sure that you can include x in your work and stuff still, but you shouldn't include it in your final answers. If there's brackets on 0, you shouldn't have brackets. Now, increasing is where f prime is positive. So we need to find f prime. And so you multiply 4/3 in front, so you get 4x to the 1/3. Multiply negative 2/3 in front. 3 goes in that 4 times, that's going to be 8. Positive 8x to the negative 5/3. And then we're going to set this equal to 0 undefined. Should label it. We should write equal 0 undefined. Now, to factor this is where some people are still having a little trouble. You always want to factor out the biggest common number and the smallest common exponent, smallest. So you want to factor out the negative 5/3. Now, when you factor it out, you're dividing it. So x to the 1/3 divided by x to the negative 5/3. Rules of exponents say you're going to subtract negative 5/3 from 1/3, which gives you 6/3 positive, which is the same thing as x squared. So x equals 0 is a critical point because it gives you division by 0 in the derivative. And x equals plus or minus I root 2, which we're going to throw out, but I want to see the work for it. Okay, so we have that. We're going to do a line check, f prime of x. And we plug 0 on it, and we test a value, x equals 1 in the derivative. Now, I like testing the factor version because it's quick to figure out if it's positive or negative. Now it's going to be positive. Negative, it's going down, it's going up. This is a relative min. We're looking for this is decreasing, this is increasing. We were looking for increasing specifically. So the answer is 0 to infinity. Now, usually it would have a bracket because we include endpoints for increasing, decreasing, but because of the domain, it should be a parenthesis this time. Inflection points. So inflection points where f double prime changes sign. So we got to find the second derivative. So I'm going to use the first derivative before we factor it. That's easier to work with. So multiply by 1/3, you have 4/3. X to the negative 2/3 minus 40/3 x to the negative 8/3 equals 0 undefined. And so then we're going to factor it, f double prime of x take a 4/3 x. So that's the biggest number they have in common. And the smallest exponent is -8/3. If you pick the right thing, you shouldn't have negative exponents in here when you're done. If you do it right, then I probably am going to design it so it works out good. This is going to be to the x to the positive 6 thirds. -2/3 minus -8/3 is positive 6 thirds. Minus 10. So that's a 2. So x equals 0 and x equals plus or minus square root of 10. Don't forget the plus or minus. This is, that's going to be an even power. That's going to be a balance, okay? So if we did a line check, if you're looking for concavity, like we don't really have to. I already know these are your inflection points and that one is not because it's not going to change sign. But if you're looking for concave up or concave down, you would do this work next, and this could support the work we're doing here. Don't forget that. You're going to test a value x equals, this is like 3 point something, so I can go with 4, positive, negative, negative, positive, concave up, concave down, concave down. And so, and we wouldn't include the endpoints for concavity, okay? Because they actually, you would break, if they said concave down, you do -√10 to 0 and then 0 to √10. It's not concave down at 0. It's neither. Okay. So inflection points are just going to be x equals -√10 and positive √10. And keep in mind the domain. That's another reason you would never have 0 in this answer anyways, is 0 is not in the domain. But even if it was, you still wouldn't include 0 in that answer. Now we got some trig, relative extrema. That's maxes and mins. Okay, so the first thing we can do is take the derivative. Any domain issues with trig? No. It's going to be 2 cosine 2x plus 1 equals 0. Undefined. Cosine's never undefined, so we don't have to worry about that this time. We're going to solve for the trig, subtract 1 and divide by 2. Alpha equals, when does cosine equal 1/2? Starts at the top, 1 √2, √2, 1/2. It's that later angle, 0, pi over 6, pi over 4, pi over 3. It's negative in quadrants 2 and 3. You got to be good with the trig, guys. So then 2x equals, quadrant 2 is going to be 2 pi over 3 plus 2 pi k. And quadrant 3 is going to be 4 pi over 3 plus 2 pi k. We're going to divide by 2. And then we just want the answers that are between the endpoints. So pi over 3 and 2 pi over 3. That's going to be it. Those are your critical points. So we do a line check. We'll label the line check. Put your endpoints on here. Test a point. X equals 0 is my favorite trig point to test, as long as it's not a critical point. So plug it back in the derivative. Cosine 0 is 1. That's positive, negative, positive. Increasing, decreasing, increasing, increasing, decreasing, increasing. This is clearly a relative max. So, and this is a relative min. So we have a relative max at x equals pi over 3, and we have relative min at x equals 2 pi over 3. That's how you do it. All right, find the exact values of the relative extrema. They're asking for y values here. You got to catch that little subtle thing. Usually we're asked find the x coordinates of where the things are located. Here the actual values are the y values. So we got to take the derivative. Now this is going to involve product rule, x squared. And a lot of people kind of messed this up. Derivative e to the negative 3x is e to the negative 3x, and then times the derivative of what's inside is going to be negative 3. You got to take the derivative of that and multiply it. Plus e to the negative 3x times the derivative of x squared is 2x. And I'm going to set equal to 0 undefined. Now I'm going to clean this up. In fact, I'm going to start factoring it. I'm going to factor out an x and an e to the negative 3x because they have both of those. And then this one just has a minus 3x left, and this one has a plus 2. So x equals 0 is a critical point. That can't be made 0. X equals 2/3 is a critical point. So those are your critical points. We do a line check, label it, put these on here, test a value. X equals 1, negative, positive, negative, decreasing, increasing, decreasing. Now, I forgot, any domain issues here? No, not this time. So this is relative min, this is relative max, but they asked for the exact value. So what we need to do is plug these back into the original equation. So 0 squared times e to the negative 3 times 0. Well, that's 0, that's 1, but it's going to be 0. That's your relative min, f of 2/3. It's going to be 2/3 squared e to the negative 3 times 2/3. So that's going to be 4/9 e to the negative 2. I don't want negative exponents my final answer, so we're going to say 4/9e squared. So the relative max is that 4/9e squared at x equals 2/3. The relative min is 0 at x equals 0. Those are good, thorough answers. So that's how you do it. Now, just because it's not on the corrective does not mean it's not on the retest. If it was on the test, it's on there. So I don't think I see any mean value theorem stuff on here. So for derivatives, that was on the test. So you need to make sure you're ready for that. I don't see any absolute max or min problems on here with the functions, but that was on the test. So you should probably expect it on the retest. So let's see, decreasing, that's where f prime is negative. Concave down is where f double prime is negative. So we need the first derivative. Natural log is 1 over what's inside, but then you have to multiply by the derivative of what's inside chain rule. And if you get multiple fractions, try and combine them all together in a single fraction, least common denominator, equals 0 undefined. This should be part of your work. You should label it. You should write this stuff. Now 0 right here is going to be x equals 0. So x equals 0, x equals plus or minus I, we make it divine, but we're only looking for real value. So then we're going to do a line check, label it, test a value. Now, what's the domain of this? This is a good domain problem. Natural logs always have issues. So the inside has to be greater than 0, which it always does. It's all reals, right? Even if you plug the 0 and negative positive in for x, it's still going to be positive, still going to be true. But better check. So we're going to test x equals, I don't know, let's say, we could say 1. It'd be natural log of 2. Wait, no, plug it into the derivative. Let's keep positive, negative, decreasing, increasing, relative min. So decreasing on negative infinity to 0, and we usually include the endpoints unless there's some reason not to because of domain. Okay, concavity, we need second derivative. So second derivative, I guess you should probably do quotient rule. I think you could try and avoid it, but I don't know if it's worth it. Low d high minus high d low all over low squared. So that's going to be x squared minus 4x squared. Okay, it's going to be 2x squared minus 4x squared. So negative 2x squared plus 2. And so the top, if we set that equal to 0, x squared equals 1, x equals plus or minus 1. The bottom gives you x equals plus or minus I. So we're not going to use those. So these are your potential inflection points. So then second, I'm going to do a line check. Negative 1 to 1. Test a value. X equals 2. That's going to be negative, positive, negative. Concave down, concave up, concave down. Inflection point, inflection point. So if you want concave down, that's going to be negative infinity, negative 1. We don't include the endpoints, and 1 to positive infinity. Okay, like I said, there's a couple other topics that weren't on here. Absolute maxes, mins, mean value theorem. Okay, optimization. This is the other part of the test. So a wire of length 12 inches can be bent into a circle, bent into a square, or cut into two pieces to make both a circle and a square. How much wire should be used for the circle if the total area enclosed by the figure is to be maximized or minimized? This is kind of like one of the projects. It's kind of like the hanger project. So we've got to draw a picture. We got a circle and a square. Square has sides S. This is a restriction on the perimeter of the objects. And then we have the, but then we're also looking for the area in here, pi r squared, and the area of this is side squared. Now, we want to get these in, so the thing we're trying to maximize, the total area, need a formula for it. So it's going to be pi r squared plus side squared, but we want it all in terms of one variable. So you can either say s equals 2r or no. Sorry, no. We can't do that way. Sorry. So the way we get it all in terms of one variable is there's another restriction for the perimeter. And the perimeter is the circumference, 2 pi r, plus 4 sides. And it's supposed to add up to 12. Now, we want to get it all R, all S. It does say how much wire should be used for the circle, which means R seems to be more convenient for that. But, yeah, I don't know. They're both kind of messy, I feel like. So I think we want to get it in terms of all R. That's going to be a little easier this time for what we're trying to answer. So 4S equals 12 minus 2 pi R. Divide by 4. So S equals 3 minus 1/2 pi r. And so we're going to plug that into the other equation. So now A equals pi r squared plus 3 minus 1/2 pi r squared, all in parentheses. So we should probably, we got it all in terms of one variable, which is, that's one of your first goals on optimization problems. But I think we want to simplify it before we take a derivative. So we don't have to do chain rule necessarily. So this is going to be 9 minus 3 halves, 3 halves, 6 halves, 3 pi r plus 1/4 pi squared r squared. And so there it is. That's your equation in terms of one variable simplified. So now we need to find critical points, take a derivative, 2 pi r minus 3 pi plus 1/2 pi squared r. And I'm going to set it equal to 0 undefined. And solve for r. So to get these r's by themselves, the easiest thing, because their coefficients aren't like terms, is to factor the r out. Don't forget this pi has a squared on it. Move the 3 pi to the other side, and then finish solving for r. Now, I don't want complex fractions. So we multiply top and bottom by 2. So r equals 6 pi over 4 pi plus pi squared. That's your critical point. Okay. Actually, we could simplify that. We could divide a pi out of everything on top and bottom, which I think is worthwhile. So let's do that. Okay. Now we got to figure out what the endpoints are, which is often, a challenging thing. Depends on the variable that you got everything in terms of. So in R, R can be negative. Could R be 0? Yes, because we would still have area from the other one. If it was a single shape, and we had to have a certain amount of area or something like that. Or what's the biggest arc be? Well, it's usually when the size of the square is the smallest. So what could S could be 0. If S is 0, here's a relationship up here between that. If S is 0, then you would say 0 equals 12 minus 2 pi r, and r would equal 6 over pi. 6 over pi. So those are your endpoints, and they are definitely endpoints. So we could use extreme value theorem, which we want to is whenever possible. So extreme value theorem, R, make a table, endpoints, critical points. I'm going to plug them into the area formula, probably the one that has all R's. Now, these, if you plug 0 in, we can do that, you're going to get 9. If you plug 6 over pi in, I think it might work out nice. So that would give you 36 over pi plus 9 minus 18, right? Plus, here the pi gets squared, cancels that. 36 over 4 is 9. So you get 36 over pi because that all cancels out. This one is going to be hard. So I would plug it in my calculator. This is something I'd for sure let you guys use a calculator. I don't think I'm going to give you something this messy on the retest. But the answer through decimals is 5.040, 5.041. As much as possible to keep things exact. So the value of this is 36 divided by 3 is about like 12, right? Or you can use a calculator. It's 11.459, but I think that's a rough enough estimate. So this is your max and this is your min. So we asked to do the max and the min. It's all the same work though. So we're going to say the maximum area is 36 over pi. Let's keep it exact if possible. I mean, I guess we could do decimals. 11.459. The units are inches squared. It was inches on here. Okay, so we got to write the answer. When, you guys describe when it happens, when the radius of the circle is 6 over 4 plus pi. Now, they really said how much wire should we use for the circle. Sorry, 6 over pi. Now, that scenario right there, 6 over pi, that happened when we used all of it for the circle. So r equals 6 over pi inches. All the wire is used for the circle, 12 inches. By extreme value theorem, so I want you to name it. Don't abbreviate it. Extreme value theorem. Tell me how it works by checking endpoints and critical points. So that's the max. similar. The minimum area is 5.040 inches squared when r equals 6 over 4 plus pi. Now, what's the circumference for that? So the circumference, which is the amount of wire we're supposed to use for the circle, is 2 pi r. That's r. So it's going to be 12 pi over 4 plus pi. Right? So inches, 12 pi over 4 plus pi inches of the wire is used for the circle by extreme value theorem. Checking in points, square points. Okay, now we could have used a first derivative test approach because there was only one critical point. That's kind of like one of the things. And it would turn out that, it would lead us to a single relative min, which would clearly be the lowest point of the graph. But defending that's hard. I wouldn't suggest it, and it doesn't always work either. So we only use that approach, I think, when extreme value theorem is impossible or it's just crazy bad itself. And this will be an example of when we have to do that. So a closed rectangular container. So it's like a box and it's closed. So that means it has a lid. It says has a square base. Okay, square base, but not necessarily the height being squared. It's a rectangle. Volume of 2,000 cubic centimeters. So that sounds like a restriction. It costs twice as much per square centimeter for the top and bottom than does the size. The top and bottom material is more expensive. So find the dimensions with the least cost. So we're going to have to come up with a cost function, but it's per square centimeter. So we've got to find the areas of these. I'm going to call these x. All these are x. The top and bottom squared the same. The height's going to be h. So the top is x squared. The bottom is x squared. The sides are xh, and there's 4 of them, right? So there's 2x squared area top and bottom times, it says it costs twice as much. Now I'm just going to go with the bottom. The sides cost $1 per square centimeter, and the top is double at 2. Now I'm going to go back later. I think it's easiest if you make these 1 and that 2, and then we can kind of just use that to get a relative price. So times $2 plus, there the sides, there's 4 of them, 4xh times $1. So that's your cost function that we're trying to minimize. So we need to get it in terms of a single variable. And so there was this restriction on the volume. The volume, which would be length times width times height, which is going to be x times h. So it's going to be x squared h is the volume. And they said it has to be 2,000 cubic centimeters. So now we get this in terms of x or h. I think it's going to be easier to get h. And then you don't have square roots and stuff. So there's h. So we're going to plug that in for h in here. So our cost function is now 4x squared plus 4 times that, it's going to be 8,000 over x. So there's your cost function. We're going to take the derivative, 8x minus 8,000 x to the negative 2, unless you really like quotient rule, even when it's easy to avoid. So that's a derivative. We want to get it all in terms of one fraction. Some of you guys weren't doing this on test. So we're going to multiply top and bottom by x squared. So we get 8x cubed minus 8,000 over x squared equals 0 undefined. All right, and then that's what we're going to solve. So the top, if we set the top equals 0, and undefined comes from that. So the top, it's going to be 8x cubed minus 8,000 equals 0. It's going to be 8x cubed equals 8,000. It's going to be x cubed equals 1,000. And cube root of that is going to give you 10. The top is going to be x equals 0, but watch out, it's repeated even number of times. So these are our critical points. Now our endpoints, everything is in terms of x. Could x be 0? X isn't going to be negative. Could x be 0? No, it can't, because then you don't get a volume. The volume has to, if x is 0, the volume is 0, and it says it has to hold 2,000. What's the biggest x could be? Well, what's the smallest h could be? Could h be 0? No, h cannot be 0, but it can go towards 0. As h goes to 0, x blows up and goes to infinity. So there's no endpoint there either. So we don't have any endpoints, so we can't do extreme value theorem. Now we could kind of take a similar approach and use like a table to, kind of analyze what's going on. We could say, okay, let's plug x in here. Cost 4x squared plus 8,000. But this is going to be hard to defend. You can say, well, what's the limit as x goes to 0? Then the limit of the cost as x goes to 0 is going to, that's going to go to 0, and it's going to go to a positive infinity. And then you could plug the critical point in, 10. That's going to be 100. That's going to be 400 plus 800 equals 1200. And then you can say, well, what's the limit as x goes to infinity? Well, as the limit as x goes to infinity of the cost is going to be, that's going to go 0, and that's going to blow up. It's going to go to positive infinity. So these are blowing up on the side. So this has to be the min. There is no max. Okay, but that's hard to defend. So the other idea is to kind of take a first derivative test approach. So we can't do EVT. We cannot do it. I mean, we could figure it out. Now, first derivative test, you do a line check and you put the critical point on there. You have this other critical point. You test a value of x equals 100 into the derivative. So I think that's going to be positive, negative, negative. Okay, now this is a relative min, right? We're not going to consider these values. They don't make sense. Here it's decreasing, increasing. This is a relative min, but it is also clearly the lowest point the graph is ever going to reach. But how do you defend that? How do you put that in the wording? So, we found it. I mean, even if you do it this way, you could plug the 10 back into the cost function and find the cost. Now, the cost is actually not 1,200. The least cost is, remember the price we were doing is 1,200 times the unit cost of the sides, because we just kind of assumed it was 1 just to make the work easy. When now I made up these variables, so I should write it in terms when the sides of the base are 10 centimeters each, and the height is, now the height 2,000 divided by 100 is 20. H equals 20 centimeters. So that's the answer. Well, how? Since C has a critical point at x equals 10 and C prime is negative on the interval 0 to 10 and C prime is positive on the interval 10 to infinity, C must have a relative minimum at x equals 10 by the first derivative test for relative extrema. Okay, so that justifies its relative min. And since C is always decreasing for x less than 10 and increasing for x is greater than 10, this must also be the location of the absolute min. So anyways, yeah, you don't want to have to justify this if you don't have to. We had to that time. Okay, all right, next one. A man floated in a rowboat 1 mile from the straight shoreline, large rig. A town is located on the shoreline 1 mile from the point on the shoreline closest to the man. As suggested in company video, tends to row in a straight line to some point P on the shoreline and then walk the remaining distance. To what point should he row in order to reach his destination if he can walk 5 miles an hour and row 3 miles an hour? So here he is walking. I like to label the picture. Here he's rowing. He's walking at 5 miles per hour. He's rowing at 3 miles per hour. We got to create a variable somewhere. This is the best place to put it. X is the cleanest place. So then this is 1 minus x. And then this is the square root of x squared plus 1. If you put x here or here, or here, it gets messier, I think. So we're trying to do least time, so we're trying to minimize time. D equals RT, so T equals distance over rate. So our time is going to be distance walking over rate walking plus distance rowing over rate rowing. So distance walking was 1 minus x, and the rate walking was 5. The distance rowing was the square root of x squared plus 1, and the rate rowing was 5. So that's your time function, and it's already in one variable, so that's nice. So we're going to take the derivative of this to find critical point. So this is going to be, I mean, you could write this as 1/5 minus 1/5 x plus 1/3 x squared plus 1 to the 1/2 power. So that's a little more friendly for derivatives. So it's going to be negative 1/5 plus 1/6 x squared plus 1 to the negative 1/2 times derivative inside is 2x chain rule, which cancels with the extra 2 that we got in front. Now, we're going to set this equal to 0 undefined, but this has multiple fractions. We want to combine it all into one big fraction. Otherwise, you're going to lose critical points. So least common denominator would be 15. So it's going to be negative 5 plus 5x. Oh, actually, sorry. Maybe we should rewrite this first. So this is going to be negative 1/5. And then it's going to be x on the top, 3 over the square root of x squared plus 1 because it's negative x1. So least common denominator, we're going to multiply top one of this one by 3, that. So it's going to be negative 3 square root of x squared plus 1. We multiply the top of this one by 5, so it's going to be 5x all over 15 square root of x squared plus 1 equals 0 undefined. So we're doing a little bit of messy algebra here. At this point, 0 is going to come from the top, undefined is going to come from the bottom. The bottom, x equals plus or minus I, would give you undefined. Well, we're not going to consider that. The top equal to 0. I'm going to square the top and the bottom. So we're going to get 9. You can distribute it inside to the x squared plus 1. 25x squared. Keep going, solve it. So we got to take the square root of both sides, plus or minus. I need to see the plus or minus in your work, plus or minus 3/4. Those are your critical points. Now, what are the endpoints? So the endpoints for x shouldn't be negative because then you're walking backwards, and then that means you're making up time and stuff. So x equal can be 0. And the biggest x could be would be 1, because we're not going to go past the town and then walk backwards. We're not going to row backwards or walk backwards because the math will actually give you time when you do that. And clearly those are outside of what we're entertaining as possible answers. So we have endpoints and critical points. So I would do extreme value theorem. I wouldn't use some other weird approach like we had to last time. I don't want to plug in a t prime. I want to plug in a t. So that was 1 minus x over 5. I like to write this here just to make sure I calculate, put these in the right thing. So we have 0. We have negative 3/4. We have 0. We positive 3/4. And we have 1. Well, we're not going to bother calculating the negative 3/4 because it's outside the endpoints. We didn't know that at first. It shows up in our work. If you plug 0 in, you get 1/5 plus 1/3. It's going to be 3/15 plus 5/15 is going to be 8/15. Okay, a little bigger than half. Okay, if you plug in 3/4, you're going to have 1/4 over 5 plus 9/16 plus 1 over 3. So it's going to be 1 over 20. These comes down to be 16. That'd be 25/16, which the square root of is 5/4. And so we get 1 over 20 plus 5/12. So least common denominator would be 60. So it'd be 3 over 60 plus 25 over 60 would be 28 over 60. 14 over 37 over 15, 7/15. Then we plug 1 in, and we get 0 plus the square root of 2 over 3. So the answer is square root of 2 over 3. Now, I need to be able to compare these all together. And I mean, I could estimate them in my head, but these end up being pretty close to each other. So this is where I would let you use a calculator just to make sure. And, write down the decimals you get. I don't want decimals in the answer, but you can write down the decimals you get and show them in your work to help me, understand how you got it. So here's the max, right? And this is the min. And so we're going to write the answer. The least time is 7/15. What are the units? Hours. When he rose to a point x was the variable, 3/4 of a mile down the shore by extreme value theorem. by checking endpoints and critical points. All right, there we go. Make sure you're ready for your retest. Like I said, make sure you study absolute maxes and mins for the other part of the test and mean value theorem for derivatives. That is it.